Welcome back to Cancers 101, the podcast where we break down the science of cancer. I'm your host, Ritika, and today we are diving into the fascinating world of epigenetics, aging, and cancer. Thinking of the epigenome as a set of instructions over time as we age, these instructions can get a little messy, leading to mistakes that might increase cancer risk. And just like a worn out map, these changes can lead us into a unknown and dangerous territory. I'm joined by Aditi today. So let's navigate this together and let's see where the map leads us.
Thanks, Ritika. I'm excited to explore how the epigenome, aging, and cancer are all interlinked. It's like discovering hidden paths that shape who we are at the cellular level.
Exactly, Aditi. So if our epigenome is a map, what happens as we age? How do these epigenetic changes accumulate over time and how do they connect to cancer risk?
Well, think of aging like a tree. As it grows, it gains more branches, some sturdy and others weaker. Similarly, as we age, epigenetic modifications like DNA methylation or histone changes happen gradually. These changes regulate how our genes work, but over time, they can lead to disorder. The more these changes pile up, the harder it becomes for our cells to regulate key processes like growth or cell death, which can eventually lead to cancer.
So it's like the tree's branches can become weaker and more prone to breaking. The epigenome becomes less stable with age, making cells more susceptible to mistakes. But Aditi, how does epigenetic drift factor into this? Like it sounds like a natural course of events, but with some unintended consequences.
Exactly. Epigenetic drift is like the slow shifting of a river's course over time. Initially, it might seem like a minor change, but over time, it leads to big differences. As cells divide, random epigenetic changes accumulate, altering how genes are expressed. Some genes might turn on the others off, and this can lead to activation of oncogenes or silencing of immunosuppressor genes, making it easier for cells to go rogue and develop into cancers.
So if epigenetic drift is like a river changing course, it means the body's gene regulation becomes more unpredictable, right? Now, Aditi, we have talked about aging and how drift can promote cancer. But how do certain organs get more affected by these changes than others?
Great analogy, Ritika. Some organs are like more vulnerable landscapes. Tissues like breast and lung are more exposed to external environmental factors like hormonal changes or smoking, which can trigger epigenetic changes. These tissues undergo more frequent epigenetic alterations that can increase the likelihood of cancer. The epigenetic landscape of each tissue is shaped by its local environment, making each organ more susceptible in its own way.
So the organs themselves can be seen as terrain that's more or less prone to erosion depending on the external forces at play. Now let's shift gears a little, Aditi. You mentioned epigenetic clocks earlier. Can you explain how these clocks work and how they might help us to predict cancer risk?
Sure, imagine an epigenetic clock like a watchtower, keeping track of the biological age of cells. It works by measuring DNA methylation patterns which change over time. These patterns act as a timestamp on the cells, reflecting their cumulative exposure to aging and environmental factors. If the clock shows that a cell's age is advanced, it signals that the cell may be at higher cancer risk due to accumulated epigenetic damage.
So, an epigenetic clock is just like a watchful sentinel, keeping track of how far the journey's cells have come. And when the time is right, it might alert us to potential cancer risk. But can these clock also tell us different treatment effectiveness, Aditi?
Absolutely. Epigenetic clocks can be used to monitor cancer treatments. If treatment is working, it helps re-regulate the epigenome, like putting a clock back on track after a malfunction. So, as tumor cells respond to therapy, their epigenetic age could decrease, showing that the cells are becoming more regulated and normal again. This could be a great way to track the success of treatments and even detect reoccurrence earlier.
The epigenetic clock does not just mark time but also provides insights into how well the cells are responding to therapy, if I'm not wrong. It's like getting a report card on how the cancer is adapting. So, Aditi, before we wrap up, what's the key takeaway that our listeners can get from this?
So, the key takeaway is this: epigenetic changes accumulate as we age, and these changes play a crucial role in cancer risk. Epigenetic clock provide us with a powerful tool to not only predict cancer risk but also monitor treatment progress. They could be the future of personalized medicine and early detection.
Thank you so much, Aditi, for sharing your expertise today. And to our listeners, thank you for tuning in. If you enjoyed this episode, be sure to share it and subscribe. We'll be back with more insights on cancer and the science behind it. Until next time, stay curious and keep exploring.